We're now going to discuss a reasonably complicated topic called thread local storage. So essentially, the idea is as follows. Let's suppose that you are just summing a bunch of integers. So you have a variable called sum with a value of 0, and then you do a parallel dot for. Let's suppose we want to count the sum from 1 to 1,000. So we put 1 and 1,001 here, and then we specify the lambda. So in the lambda, for example, what we can do is we can increase the sum. Now, sum is a shared variable. It's shared between every single thread that will want to increase it. So if you do want to increase it, you have to do something like interlock.add, do ref sum, and increase it by the value of x. So this is how you would do it. Unfortunately, the problem here is that there is a lot of access to the sum variable. So every single task is doing the access at every single point. Now, why can't we calculate a partial sum on each of the tasks and then just add the partial sums using interlock? That will certainly decrease the amount of interlocked calls necessary. And in fact, what happens is the .NET Framework gives you such a functionality. And it does look a bit complicated, I have to add. So that's what we're going to see right now. So we'll do a sum once again. Sum equals 0, and there'll still be some interlocked code, but for the most part what the parallel loop is going to look like is completely different. So first of all, and we're going to take this slowly, the parallel loop is going from 1 to 1,001. So we have 1,000 elements. However, the next argument is going to be something completely different to what we've seen before. You can see that the parallel 4 has lots and lots of overloads. There is a huge number of overloads here, and if you fire up code completion, you'll see that there are plenty of different options here. So the option that we are actually after is the first one, and you might be surprised that there is no arguments in a lambda here, and that's because this lambda is an initialization lambda for thread local storage. So the idea is that for each of the separate threads, you can have some sort of storage which is local only to that thread and not accessible to other threads. So the idea is that instead of doing interlocked on the sum 1,000 times, which is inefficient, what we can do instead is we can take each of the threads and calculate the partial sum. So the sum of the range from 1 to 1,001 that's been allocated to that thread, we calculate the sum in an ordinary fashion without any interlock calls. And when we got this partial sum, that's when we do the interlock. So the initialization of this sum is done using this particular lambda function, and we initialize the local storage value with a 0. So that's the value that each of the threads is actually going to increase. Now, the next part is, of course, how you update whenever each of the threads execute. So the lambda for the update part is fairly complicated. Instead of taking just one argument, which is the counter, we now take a whole 3 arguments. So the first argument is in fact the counter. That's the value of x. Now the second argument happens to be the state variable. That is the variable that is actually being used to show the state of the parallel execution. We cannot avoid having this variable even if we don't care about using it. And the final argument, and that's critical, the final argument is the current value of the thread local storage. Let's call it TLS. So when you execute this in separate threads on each of the iterations, what's going to happen is TLS will be initialized with the current thread local value. And then, of course, what you can do is the following. So let's put the actual lambda in here. What you can do is you can, first of all, increase the thread local storage value by the value that you have here. And notice that on the thread local storage, we don't have to do interlock because it's thread local. Nobody else is actually accessing this particular variable. So we can just increment it in an ordinary fashion without using interlocked or any kind of locking. And then what we do, and this is also critical, is we return the new value. So we return TLS. And this basically means that as we kind of execute this iteration, all those times, we keep updating the local or thread local variable. Now, somewhere down the line, you're going to be in a situation where you've executed all of these parts and you want to take all of the thread local variables and add them to sum. And that's exactly what the last part is. So the last part basically takes a partial sum in our case. So that's the thread local variable that you get at the end of all the executions after they've all been executed. And then we can interlocked dot add ref sum partial sum. Now this is great, and this is how you get to essentially speed up the parallel loop. So let's right line the final value. So I'm going to say that the sum of 1 to 100 is equal to sum. But in addition, what I'm going to do is I'm going to add a bit of debugging code so that we can see what's going on. Because if I run this, you will get the correct result, which is 500,500. But let's actually get some console write lines in between so we can see what's happening. So in each of the iterations, I'm going to add a console write line, which basically says that task.currentID has this sum, and then taking the sum thread local storage. And then of course when we do the partial sums, I'm going to once again write line, and this time round what I'm going to say is I'm going to say that the partial value of task.currentID is, and then once again output the partial sum like so. So now we're going to get a lot more information about what's going on. And what you can see is that each of the tasks, as they execute, they get their sums, and then eventually these partial sums, once the task has completed, so task 20 has completed, it's got its own local sum of 10945, that gets added to the final sum using interlocked, and that's what we get as the output. So this is how you can reduce the number of direct accesses to the final variable, instead doing it in a kind of stepwise or partial way by computing the partial sums first of all, and then adding those partial sums in a safe way to a shared variable.